Hello, today I'm going to show you the inside of IGBT Arc Welder, MMM, and of course it's a cheap model from China. And so we're going to take the look inside of it right now and see you back. Here we have the inverter itself, basically. The complete unit basically, and all of its parts. Now let me explain a little bit how this works. Mains comes from here basically. That's not the original power cord, because the original power cord was not very good quality. Even this one, it's not the best power cord for arc welder, but we'll get a better power cord and I put it soon. But for now this is just so we can test it. It's much better than the original one. So it goes into the switch basically. No AMI filtering here. There should be one, but it's made in China, so they don't care. Hell, I also don't care, so no AMI filter. At least in this instance I don't care. And the ground is disconnected in the moment here. That was also not original. I put this one because the original one was just a soft tapping screw and that's not so good. But for now it's disconnected because we're going to do some measurements just to make it extra safe. I disconnected the RF here and it's run from isolation transformer, so that's safer like that. Basically we have here a 30 amp relay and a NTC, right? Yes, NTC. NTC basically in the limit inrush current to these capacitors. Where are they? Here. Basically we have three 470 microfarad 400 volt capacitors in parallel. The full bridge rectifier right here. The mains go straight into this one through the inrush limiter, of course, and charge those capacitors. Then we have here the half bridge. That's two parallel transistors, 40 amp 600 volts. Then we have here the next thing, we have the output diodes. That's actually 4 diodes, but we're going to take a look at the schematic soon. Our divider capacitors for the half bridge, our main output transformer, measuring shunt, control electronics of course, and on the front panel with the potentiometer for controlling the current, power LED, overload LED, and the display. But that the display shows is of course completely useless because this inverter is, I guess, 140 amp because the name. We will take a look at this soon. And this shunt is for 180 amps. So I think it's a 140 amp inverter, but in the front it says 400 amps. It's of course a lie, but it's made in China, so that's normal for China. And let's take now a look at the schematic, and then we will take a look at the waveform of the primary transformer, this one, and the open circuit voltage on the inverter. And before that, the control electronics is considered from this PWM controller. It's a UCC 3525, small auxiliary power supply here. It's VCE basically. You can probably read the number and Google that if you want. Very powerful fan here in the back, 7 watts, I think 5000 RPM, so very powerful, very loud actually, but that's okay. It's a welder, so it doesn't have to be silent. There is a gate drive transformer in here, but you cannot see it. I have some photos from the bottom that you cannot see now. They will be put now here, and I see you now on the schematic. Okay, we are here now at the schematic basically. We have here our NTC inrush limiter as I was shown, and the relay that bypasses it. Life and neutral goes straight here from the switch. I didn't draw the switch. Rectifier. 3x 470 microfarad 400 volt capacitors parallel here. The half bridge actually considered of, oh that's out of focus, sorry. Considered out of two PT40 T60 IGBT 600 volt 40 amp, 2 in parallel on each side, so 2 on each side, that's 4 in total. The divider capacitors are 2 times 5 microfarad each. At least I measured it in circuit, so I cannot read the reading on the capacitor. I think it's 5 microfarad each, would make sense because I measured it, because it's a bit hard to measure in circuit because of the electrolytics here. The current transformer is 1 turn primary. I don't know the secondary, maybe 50, maybe 100. I guess 50 or so. I don't know. Or more, I really don't know. The main transformer is here. It's a 13 turns primary, 5 times 5 because it's central tapped here. Here is the measuring shunt, measuring the output current, 180 amp shunt basically. And the diode that I was stock, it says 60 and 20. Now I cannot find a data sheet, but I guess it is it's a double diode basically. I guess 2 times 60 amps, so 200 volts, so 2x on each side, so that's 4 60 amps diodes basically parallel, so 240 amps would be maximum, but they want to have probably some safety in here, so it's like, I think the output is 140 amps. I did not measure it yet. We will do that in a next video because this will be long and then no one likes to watch long videos, so next part will be the test of the output current. Based it's the output, no inductor here. I would like to see an inductor here, but there's no inductor, maybe we add that one. I draw only the power electronics, the control I completely omitted because that's too complicated to reverse engineer it. And this is what it shows on the board. It says ZX740DBZKB. That's the 140, I think that's a 140 amp model. When I Google this, I find some similar board that says 140 amps. Version 1.2, 2017. I guess that's the year when it was designed. And now we're going to take a look at the waveforms and output voltage, and next video will be current test, and I will hopefully get a better lead in there. Yes. We're back here. We're going to increase the voltage to 230 roughly. And I'm going to turn it on, and we are going to probing here across the primary transformer. We're going to see the waveform on the primary transformer, and the output voltage we measured here on the output of the rectifier and the circuit board basically, because it's easier than clipping there, because that's big screw there. My clamp cannot fit that big connector basically, or screw. So let's turn it on and see the waveform. Roughly 350 on the reach or on the transformer side, and peak to peak and frequency is 46 kilohertz, and open circuit was from 68 to 7 volts. And in the next video we're going to make a load test. The front panel is this. The waveform does not change if I turn the so that's only under load, then it controls that. And that's all for now. It runs quite a long time after I switch it off. Seems to be very efficient. And yeah, in the next video I get a better cord and we make a load tester basically. some carbon arc test basically. With better cord I mean simply one with thicker isolation, because this is 3 times 2.5, so that's enough for the current, but the sheet that's like very thin. It's like a reduced sheet thickness for like softness, and because it's for installing inside of machines, basically this kind of cable. It's I think it's it says right here, it says, oh, you cannot read that, no way. Yeah, you can read it now. Lab cable, Stuttgart Allflex Smart 108 3x 2.5 square. Basically that's it, and thank you for watching, and see you next time. Bye.